Okay. Oh, hello. Wow. Okay. I actually wasn't expecting you to be here, but that's okay. That's good. Let me just post this link. Okay. So, I want to start working on some of the extraneous proofs to put in appendices, but we're going to start with a little bit. Oh, nice. Yeah, so we're going to start with a little bit of exposition and definitions. So last we left off, we were starting off this new section. So we had just finished integration. We have a whole bunch of stuff in integration about homotopies and antiderivatives and indefinite integrals, and a whole lot of locally convex sets. We're going to get back to that in just a second. But what we want to do is we want to, for this section, we're going to be working in a particular sort of domain for functions. So you want to try to define what that's going to be. It's very precise, and I've actually never done this before, so we'll see if this actually works out. Or rather, I think it should work out, but I've never done the proofs for it before. So that might be a little difficult. Okay, so we want to define, I'm just going to make this name up because I don't have a name for it. So we're going to have a name for a certain type of set. So let S be subset to A, so some subset of our space, and X be a point in S. Then we want to say, we want to define a particular class of contours. So define the set let's see, I used a symbol for this in my other thing. Okay. Circle sub x superscript s. So we'll define this set as the set of all contours. We'll have sigma as a contour. It'll be subset to S, but it'll also be subset to A star plus X. So this is a really interesting definition. So there's one more piece, such that the projection P1 of sigma has turning number 1 about P1 of X. So so this is a very interesting sort of definition for loops. So this class is the set of all contours sigma, which are subset to this set here. So if we just had A star plus X, this would just be the set of contours sigma such that the projection P1 of sigma never overlaps P1 of X. So that's just what this set A star plus X is. If we take A star, which is the set of all elements which are never 0 on the first index, and then we add X, so we translate the whole set by X. So it's the set of all elements which are not the same as X on the first projection. So A star is the elements which are not the same as 0 on the first projection. A star plus X is the set of elements which are not the same as X on the first projection. So this class is a set of contours sigma subset to S such that this projection has turning number 1. So it makes a loop about the point P1x one time in the in the counterclockwise direction. We also want to say and such that there is a convex C subset to S having X in C and sigma subset to C. So this is a little more specific. So this first condition is saying it's just a contour in S, but it never overlaps X on the first projection. This second condition is saying, in addition to that fact, it's also going to take one counterclockwise loop around X. And this last condition is saying, in addition to all of these other conditions, there's this convex set C, which is actually we want this to be a convex neighborhood. A convex neighborhood of X having sigma subset to that C, the convex set. So this is our definition of this sort of class of curves. So we can essentially just think of this class of curves as a sort of a generalization of the idea of a curve taking one counterclockwise loop around X. And the way that we define how it takes a counterclockwise loop is that it's with respect to the P1 direction. We could maybe make this a bit more explicit. So we could say sigma subset to S, and then we could say such that the projection P1 of S is, we could say, never equal to P1 of X and has turning number 1. So we could say, we could frame it a little more explicitly like this, but essentially it's the same idea. It's a contour in S, which never overlaps X on this first projection, and it just takes a full positive counterclockwise loop around X. And then this last condition is that we want this loop to have this convex neighborhood C, and that it stays in. So we're going to have a proof here that we're probably going to put into an appendix, but we'll just do it here for now. So this theorem is, we're going to say let S be subset to A and X be in S, then any two sigma gamma in this class of curves are homotopic in the set S cap intersection A star plus X. Or we could say in the set Y in X such that P1 of Y is not P1 of X. So this is mostly a topological exercise, but it's very obscure and specific. Let's just say hopefully this compresses it a little, makes it less gross. It didn't. Well, okay, we can just use the normal. That we were doing before. Okay, so the proof is going to be we're going to say I think what we want to do as sort of a proof sketch is, since both of these are in these convex neighborhoods, the first step that we want to do is find a way to force them into the same neighborhood. So first we want to prove that we can sort of get these into the same neighborhood. And the way that we're going to do that is just by scaling them down in the direction of x. So we'll say fix some r greater than 0, some real number. And we'll say, and consider the homotopy, we'll have f of ts defined as equaling, so what do we want to do? So we want to take the curve sigma at its point t, and we want to scale it in the direction of x. So I'll have x plus sigma t minus x times r. And actually I think because we need this to be a convex sum, oh no, actually this is a convex sum, isn't it? Yeah. Okay. Instead of r, it's s, actually. But instead of s, it's actually let me think. So we want to scale this down from at the point, so we're going to do a line. So at the point s is 0, this will be 1. And I think at the point 1, it will be r. Let me think on that. So actually we're going to say this r is in 0, 1. That's a little better. Okay, so let's see, how's this going to work? So we have x plus this difference from sigma t to x. If this coefficient is 1, then we'll just get sigma. And if it's 0, then we just get x. So that's sort of scaling down the difference between sigma and x. So linearly transferring from x to sigma. So at 0 it's x, and at 1 it's sigma. And then we have, for our actual curve, when s is 0, we want this to be sigma, so this will be 1 plus s times something. When s is 1, this will end up being, we'll have 1 minus 1 plus r, this will be r. So this will be x plus r times this whole thing. Okay, and I think this is good. If we want, we can sort of distribute this out a little so that it's less messy. Actually, no, I think it's fine the way it was. Okay, let's put this s here. Let's negate both of these. That'll negate this. I think that's fine. I think that's what we want. So, because r is in 0, 1, this 1 minus r is in 0, 1. And because s is in 0, 1, this product is in 0, 1, which means 1 minus this product is in 0, 1, which means this whole expression is in the set s, since it is, since s is convex. Okay, good. So this function is continuous, in both S and T. Oh, actually, this is a little messy. Technically, a homotopy of loops is supposed to be fixed on the edges, which is not what we have. I'm going to pretend that that condition doesn't exist for a minute, and we'll fix it in a minute. So we'll say fix r in 0, 1, so this function continues in both S and T, and it has let me think. It has f of t0 equaling, so this will be x plus this whole thing where s is 0. This will be 0, this will be 1, and they just get sigma minus x plus x. These cancel out. And also f of t1 equaling, we have x plus this whole thing. So when s is 1, 1 minus r, this is just r there. Okay, so fix some r in 0, 1 and consider this function. So since r is in both r and s are in 0, 1, I actually want to say t and s are in 0, 1. Since r and s are in 0, 1, then 1 minus r times s, actually 1 minus r times s is in 0, 1. So f of ts, that's right, and we want to say and x and sigma. Oh, right. No, we got it, okay. Fix some r in 0, 1, consider blah 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 for 0, 1. Okay, so actually we also want to do subset s b. Oops. I'm in the wrong tab. There we go. This is not where I need to be. We need to be over here. Okay. Okay, so we have our complex neighborhood, r in 0, 1, this function over st in 0, 1, rs is in 0, 1, then this is in this, and x sigma, sorry, hold on, 0, and since x and sigma are subset to C, then FTS stays in C as a convex sum. Okay. So we have also, since f is continuous, this makes it a homotopy of loops. Yes, so we're going to say homotopy of loops rather than of curves. I'm fairly certain that this actually makes sense, but let's double check that that makes sense. Usually loops need a fixed like base point. Space of based loops in X. Two loops can be multiplied by concatenation operation space a infinity space. System. Okay. Free loop space is topological space. Space of match from the circle with compact open topology. Free loop space denoted by Lx as a function of free loop space is right join blah blah blah. I don't know what any of these words mean. Yeah, you are not the only one. I don't know what these words mean. I'm trying to figure out if there's a precedent for baseless loops. Usually when you go through topology, you learn about homotopy of loops with fixed endpoints. Yeah. It was a while ago for me. I don't remember if we did. Okay. Interesting. Okay. Maybe I should just add this as a distinction. I'll fix that later. I'll just write this. And maybe eventually I figure it out and fix that. Okay, so let X be in C subset S be convex neighborhood blah blah blah. Fixation point R in 0, 1. Consider blah 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 so and so on. Okay, so we're constructing, instead of having the same type of homotopy as we had before, we're going to have a free homotopy which has free endpoints. So because these are loops, this is usually okay. we will figure out how that works in a minute. I'm gonna finish this brief because I want to keep it in my head. So okay, so f stays in C as a convex sum. So essentially we're just scaling down. F is just it's starting at sigma, and it's just scaling down this curve continuously down to in the direction of x. It's contracting in the direction of x linearly. This is valid since we're in this convex set C. Also, we can say so on. Okay, so x sigma stays in C, and then FDS stays in C as a convex sum. F is continuous, since makes it a, we want to say, free homotopy of loops. This function is continuous in both ST, and it has ft0 equals sigma t and ft1 equal x plus sigma t minus x times r. Okay. So we can say the loops sigma and x plus sigma minus x times r, and we can actually distribute this to x times 1 minus r plus r sigma. Okay, so this function is, okay, so hold on. It says in C as a convex sum, f is continuous and makes a homotopy of loops. Moreover, we have P1 F ST as equaling this whole thing, P1 of this. So this is just P1 of all of this junk. And this is P1 of x times plus P1 of this. This is a constant, so it scales through like that. And then we just have P1 of sigma minus P1 of x. And this is going to be non-zero because we're just scaling it in the direction of x, but not totally. Sorry, not zero, not P1 of x. Because we have this P1 of x. Actually, we want to say r is, well, let's restrict r is greater than 0. That's required. Right. So this is not going to be P1 of x. The only way that's going to be true, so we have this thing is non-zero. And this expression should be non-zero because if this were 0, then this would be 1. But if this is going to be 1, since both of these things are at most 1, both of them have to be equal to 1, but in that case, r would be equal to 0, which we have now excluded. So we have this is not equal to P1. Oops. Okay, so since r is greater than 0, then so we have the two loops, sigma, and let's just do this how we did it before. X plus sigma minus x times r as freely homotopic. Okay, so x is in C subset S, convex, fix some R, 0, 1, do continuous contraction, blah, blah, blah. F is continuous, makes homotopy of loops since R is greater than 0, so on and so forth. We have the two loops, this and that is purely homotopic. Okay, so this is sigma and gamma. So we're going to say let C1 and also C2 be the convex neighborhoods with sigma subset C1 and gamma subset C2 as required. Fix some R in 0, 1 and so on and so forth. So we have these two loops as freely homotopic. And then we can say, since C2 is a neighborhood of X and S, then for all, for sufficiently small R, we should have X plus sigma minus X times R as being in, actually, subset to C2. So essentially what we're saying is, so we've constructed this homotopy from sigma down to these contractions. Since C2 is a neighborhood of X and S, so we've said C1 and C2 are convex neighborhoods with these subset conditions. So these are required by this condition. We're going to fix some R in 0, 1 and consider F as being this continuous contraction. This proves that sigma is freely homotopic to this contracted loop, where we've scaled it down by R. As R goes to 0, this entire loop will tend pointwise to just X. And since sigma is continuous, it has to be bounded. So for all sufficiently large R, for all sufficiently small R, we should have this whole loop being inside any given neighborhood. So in particular C2. Okay. So this is this. So we're going to say let sigma 1 be X plus sigma minus X times R be this loop. Okay, so that's the first part. So we've shown that although we started with two different convex neighborhoods, we've created a homotopy to some contracted loop sigma 1, such that they're actually in just one neighborhood, C2. Yes. We could use a different symbol. Instead of doing sigma 1, we could just do delta, because why not? Okay, so now we can say, now that they're both in this one singular convex neighborhood, now we just have to prove that they're homotopic to each other. So I think to do this, what we want to do is we're going to construct a triangular loop, and then we're going to let me think on that. So essentially what I want to do is to reduce this to a two-dimensional problem. I think using the convexity condition, I think we can probably find a way to essentially just turn these two loops into circles on the first projection, then with some extra junk. Okay, so now we want to say since the projections P1 of delta and P1 of gamma have turning number 1 about P1 of x, we can find a homotopy anything on that. This is really hard. Gosh. Actually extremely difficult. Maybe I will just leave this for now. I'll just put this aside for the moment. And we'll get back to that later. Okay. S subset A, X and S. Define the set OXS as the contour is sigma subset S. These projections are not this, and has turning number 1 about P1 of X in the counterclockwise direction, and such that there is a convex neighborhood, this having sigma subset to C. Okay. Okay, so Okay, let's do it this way. Okay, yes. Okay, yeah, we'll just do it this way. So we're going to say a subset of A is called a proper domain when for each point x in the set S, there is a convex neighborhood x in C in subset to S, and contour sigma subset to C intersect this A star plus x, such that the projection P1 of sigma has turning number 1 about P1 of x in the complex plane. If S is a proper domain, we let sigma x S for each point x in S, we let circle sub x superscript S be the set of all contours sigma which rather we let this be the homotopy class of all contours which which are, yes, all contours which are freely homotopic to sigma over S cap A star plus x. Okay, that's better. Okay, so a set S subset to A is a is said to be a proper domain when for each x in S there is a convex neighborhood x in C subset to S and a contour sigma subset to C intersect this A star plus x such that the projection P1 of sigma has turning number 1 about P1 of x in the complex plane. If S is a proper domain, for each point x in S, we let the circle xs be the homotopy class of all contours which are freely homotopic to sigma over this set. And we're going to just add a note. This definition is well defined since any contours sigma satisfying the proper domain condition for Sx are purely homotopic. And then we'll just say this is proven in appendix C. I don't know. And I'll just add a to-do note. Okay. Okay, so this is our definition for this homotopy class. So it's just going to be these, essentially all of these loops, which can be contracted towards x without actually passing through x on this vertical segment. On the vertical, basically the points where P1 of sigma overlaps P1 of x. So they have turning number 1, and they have this overlap. Okay, so blah blah, so on and so forth. Okay, so this is permanent in appendix C. So we can say let S be a domain, proper domain, and f map S to A be differentiable. Then for each, we want to say for each point x in S. Actually, let's do it this way. Convenience, we let S sub x be equal to S intersect A star plus x, which is equivalently the set of y in S such that P1 of y is not P1 of x. Actually, let's do a superscript. Oh, that's a mistake. Okay, so for proper domain S and f mapping S on this punctured neighborhood, differentiable. We define the loop integral of f about x as follows. Okay, so blah blah blah. Okay, so we're going to say, sort of as a shorthand, we're going to say this notation, S, so S is a set, and if we have this superscript circle X, this is just the punctured neighborhood, S intersect A star plus X. So this is the set of y and s such that the first projection of y is not the first projection of x. So all the y which are not overlapping x on this first projection. So for a proper domain S and f mapping this punctured neighborhood to A as a differentiable function, we'll take any contour sigma in this homotopy class, any contour sigma in this homotopy class, and define the loop integral of f about x as follows. So this is our sort of definition. So so if we have yes, so we're doing this circular integral essentially of f of x. This lets us omit the path. So this is well defined. We could try to mess with the limits if you think it doesn't look good, because it's not like the same. But yeah, so this is well defined since f is differentiable and s is locally convex. Actually, we're gonna have to verify something else. We're gonna have to verify that this punctured neighborhood is also actually locally convex. I think it is. I think that's fine. Actually, yeah. Okay, yes, so S Lx, this is this punctured neighborhood for a proper domain S, and f differentiable on this punctured neighborhood. Take any contour sigma in this homotopy class and define the loop integral of f about x as follows. So it's this. This is well defined since f is differentiable and s punctured through x is locally convex by consequence of s being locally convex. So any the integral of f over homotopic loops is identical. Extending this to the case of freely homotopic loops is a matter of base change. Okay. All right, so now we have yes, okay, so we have this loop integral for differentiable functions, differentiable on a punctured neighborhood, on a punctured proper domain. So we're going to use this to define, we're actually just going to prove our first theorem straight away. So let's see. So our first theorem is let S be a proper domain and F map. Actually, we should probably say S is also connected. It's probably going to be useful. Okay, so S be a proper domain and F map S to A be differentiable, then for any x in S, we have this equality. So f of x is going to be equal to this integral about x of a fraction. We have f of z over, I think, z minus x dx. Okay, so we have this. I believe this is what we want. So the proof of this this theorem, it's going to be essentially, it's actually exactly the Cauchy integral theorem. So we're going to use the fact that an integral of just the reciprocal function about a loop with turn number 1 is just I2 pi. Actually, yes, that's right. We need 1 over I2 pi. One over I2 pi times the circular integral. Okay, so we can say let's think. So what we want to do is take any curve, I actually want to say find a curve sigma in a circle xs such that we have a convex C subset S, actually I want to say convex neighborhood X in C subset S. X in C subset S with sigma subset C. Then we want to say since C is convex, we also have x plus sigma minus x times r in this homotopy class for any r in 0, 1. So that means we have this integral of integral about the point x of this fraction f of z over z minus x. This should be dz. This is just the same as this integral over of this shrunken down curve. But actually we can we can take this as a limit as r goes to 0. Okay, so okay, so okay, yes. So essentially we're saying take for any r in 0, 1, excluding 0, we can shrink down this curve, contract it in the direction of x. Since our set C is convex, this curve will still be in our in our homotopy class, since they're homotopy. Since the integral of a differentiable function is constant over homotopic loops, yes, because the integrand is differentiable, we can actually just take this limit. So each one of these functions, each one of these integrals is just a constant. So if we just take this limit for r, it's just a limit of constants. Each one of these doesn't change with r; it's constant with r. But what we can do is we can rewrite this as we can translate this. So we can do the limit as r goes to 0. We have yeah, this is right. Okay, limits r goes to 0. We have this integral on right. Okay, yeah. So we can say. So actually what we want to do is to take, we're going to subtract f of x in the top, and then add the same integral, but just with f of x in the top. Right, so this integral about x, actually we can do that before we do the limit. Yes. Okay. Yes. Okay. So we start with this integral. We sort of separate out this f of x part, and add it back in. And then we can just say, well, this is just, so the first part stays the same, and the second part is just f of x times this circular integral. But this is known. Right. Okay. So let me clean this up. Not that much. Okay, right. So so what we're saying is, so we're gonna start with just this integral here. We're gonna subtract and then add f of x in the numerator and sort of split it off. And then we're going to factor out this f of x from this second integral because it's constant by z. So this first integral stays the same, and this one we just pull out this f of x, and then this one is just this integral, this loop integral about this reciprocal. But we could also say, by just doing a change of base, this is also the integral about, we have integral about 0 of 1 over x dx z, 1 over z dz, yeah. And then this gives us what we want. This is just I2 pi. Right, okay. So we do have this. So we separate out this numerator part, factor it out of this second integral, and then we do a translation to turn this integral into this circular integral of 1 over z, and then this is just I2 pi. So now now we need only prove that the remaining integral vanishes. So find a curve sigma in this multiply class such that we have this convex neighborhood. Since these convex, we also have sigma sub r, this contraction. Since the integrand, and then we have, since the integrand is differentiable, so we have this remainder integral this is the same as, so we do an integral on the contour sigma. Actually, we can do this as a limit where it goes to 0, this integral on sigma sub r, which is the contraction of the same integrand. Okay. Nice. Okay. And so now we want to show that this this whole expression is going to go to 0 very fast. How can we do that? So let's think. I think what we can do actually, is we can say that as r goes to 0, we must have our z going to x, and it must be the case. Actually, yes. Actually, that's very nice. Okay, so we can say as r goes to 0, we must have z going to x uniformly. And since f is differentiable at x, the integrand must be bounded across. Actually, we can say for each r, the integrand is bounded. Actually, we can say, further than that, continuous, and thus bounded across all x in, actually z in sigma sub r, and as r goes to 0, we must have z go to x uniformly across z in sigma sub r. And since f is differentiable, the integrand must be bounded across. So for each r, it's bounded. Actually, we can say a little more than that. We can say across all. Yes. Okay. So for each epsilon greater than 0, the set of union r greater than epsilon sigma sub r is compact, and over which our integrand is continuous, so bounded. Moreover, as z goes to x, or rather we can say as r goes to 0, we have all z in sigma with sub r having z goes to x. Actually, let's do it this way. The integrand is continuous and thus bounded across, actually we can say continuous across all z and sigma r for any r greater than 0. And as r goes to 0, we must have z goes to x. So across all z and sigma r, f is differentiable, the integrand has a limit, and we can say so from this we may conclude that the integrand is bounded, and then we can say let be in a real bound the integrand So then we have its absolute value of this integral is bounded by the length of sigma sub r times b, which goes to 0. Or we could be more explicit and just say that this is r times the length of sigma times b, and thus this limit is 0. Actually, yes, we can go even further. We can say okay. So integrand is continuous. As r goes to 0, we must have z goes to x uniformly. And since f is differentiable, the integrand has a limit. So we may conclude that the integrand is bounded across all z and r. So we can say let b bound the integrand, so then we have this approximation, which is just this, and then this limit goes to 0. We could also do it like this, limit this is bounded by the limit of this, which is just this, which is 0. And this implies that if you just take this whole integral, it's independent with r because we haven't put r there. We can just take this limit as r goes to 0, and this is just going to be f of z plus 0. And that's fine. Okay. Okay. Nice. So essentially we're just saying the reason that this works, this f of z over z minus x, this integral, is that if we pull out this f of x portion from this, then this fraction just becomes the derivative. It's limiting to the derivative. And this fraction has a known value. So in order to figure out this one, we can factor out this f of x as a constant, and then we just have this circular integral of this reciprocal. to solve this, we just translate this whole integrand. So we just do a translation or a substitution. So instead of doing a circular integral around x, we do a circular integral around 0 and just translate z by x units. But then this is just the circular integral of 1 over z. And this integral is well known. This is, since 1 over z is in particular, is differentiable on all of a star, is differentiable on c star. So we can just pick a circular loop on the complex plane. And then this is just a complex analysis problem. So we do get I2 pi. Yes, I2 pi times f of x. And then we can just divide through by 1 over I2 pi. So this would be this limit at the very end. So we prove that this derivative, this limits uniformly. And we can bound this by taking the length of the contour to 0. Actually, this is a little extra. We don't really need to do this. What we can actually say is the integrand is, we can actually, yeah, just right away. We can say converges uniformly to, we can say actually is continuous across all z in the set, and as r goes to 0, it must converge uniformly to f prime of x. Yes, and then we just find a bound, and we bound the length of the loop that goes to 0. Yes, okay. I think that is fine. Okay, so that's fine. I think this is good. Yeah, so there's a few sort of hidden assumptions here. So one of the hidden assumptions we have is that by contracting this curve sigma by a factor of r, the length also changes by a factor of r. This seems kind of unobjectionable, but it's not one of our theorems. Another one of the things we haven't proven that we used here, or rather, I guess we did prove, but we've just sort of shoved it down here, is that if we haven't finished the proof that this homotopy class is well defined, so we want to show that all of these loops are homotopic, so that if we just have some loop in some convex neighborhood of x, or some punctured convex neighborhood of x, we want to say that any two loops that are like that are homotopic to each other. Doing that is still something that we want to do. Let's see, what other assumptions do we make that we haven't proven yet? Oh yes, we haven't, whoops. We haven't proven the free homotopy for loops. Technically, that actually doesn't necessarily follow from our theorem. So that was sort of one of the assumptions we made that we sort of had hidden. But actually this does not follow, and the reason that it does not follow is because the path that the base point of a free loop homotopy takes may not be actually a contour at all. So we can't necessarily just do a base change. So I think what we're going to have to do is we're going to have to go back to the integral section and just make a note or something. We're going to have to make a note that let me think on that. So this proof for the homotopy integral ends up in this position here. Okay, yes. Okay. I think we can add this as a corollary. It says that A look like convex, simply connected, blah blah blah. Okay. Yeah, let's try that. So we can say, and instead of this having this corollary, let's do a second one. And so we can say so essentially, so what we'll do is, so we'll just say, for this proof, we'll say, this follows by modifying the previous theorem by changing the assumptions instead of having ft0, actually we want to say f0s be sigma 0, which is gamma 0. Instead of having this and f1s be sigma 1, which is gamma 1. So So this follows by the, modifying the previous theorem. So we'll say and instead have the conditions that f0s is f1s. The first portion of the proof to find n and construct h jkn still holds, and all the assumptions, actually we can say okay, yes. Also, this is messy. Let's do this. So right down here, we're gonna do this. Okay, so okay, nice. This is better. Okay, so I've modified this first proof to have this last justification at the very end. So all of this is valid. So we have this homotopy with base point. We find this partition, and then we just note we're going to label these integrals. We note that if we do this integral around one of these blocks, it's 0. And if we do this integral on just the top edge, which is where the second portion is 0, or just this bottom edge where the second portion is n, this will be sigma or gamma respectively. We add up all these loop integrals, which are all 0, rearrange the terms. We get down to here. This one's still that's a mistake. Let me fix that. So we should have I1 here and I0 here. Okay, yes. So same story. Add up all the loops, separate them out, cancel like terms, rearrange them. In this final line, so we have this one's still sigma, this one's still gamma, and this one over here. This should be, I think we need, let's see, we have, this shouldn't be J, this should be K. And this other one should also be J. Okay. Oops, J. Okay, yes. So cancel the loops, separate the terms. Let me make sure I got these right. So this one, I1 with n. We have I1 when k goes to n. That should be we have minus I0 and plus I1. I think I may have messed this one up. Let's figure this out. So this one will be the summation. Okay, the summation that's in common is the J sum, which means we'll just get the K term varying. We'll have plus when K is 0 and minus when K is N. So this will be minus there. And for the other terms, the one that they have in common is the K sum, so is a K sum. We have plus when J is N. Okay, so then this one should be a plus. And that fixes it. So everything is the same. We get down to this last stage. So this one's still sigma, this one is still gamma. And then we have this. In this proof for homotopy with base point, we justify that this is 0. So since each f0s and f1s are constant with s, it follows that the integrals I0k and I1 0k and I1 nk are 0, as they have 0 length. This proves the claim that these integrals are the same. The corollary to this, so the modification, is remove the conditions that f0s is sigma 0, which is gamma 0, and f1s is sigma 1, which is gamma 1, and instead have the conditions that f0s is f1s. The first portion of the proof to find n and to construct these tiles still holds. And all the assumptions, where are we? On the I1, I0, all the assumptions and working out of the I1, I0 integrals still holds, except on the very last line, instead of justifying I1 0k, so it should be I1 nk minus I1 0k equaling 0, since each of the component integrals are 0. We instead justify it by noting that they cover exactly the same path. So we remove these edge conditions for being the start and end point being fixed, and instead replace the condition that the start and end point are the same, regardless of what they are. It doesn't have to be fixed. The first portion of the proof to find n and construct these tiles still holds, and the assumptions in working out of the I0, I1, I0 integrals still holds, except on the very last line, instead of justifying this difference equaling 0, since each of the component integrals are 0, we instead justify it by noting that they cover exactly the same path. And it's the same proof. Nice. Okay, that's great. That's fine. I accept this. I think this is good. So we've made more explicit that, so although this first proof says these have to be homotopic with fixed endpoints, this second proof says if they are loops, then the base point doesn't matter. And that is okay, I think. Okay, that's fine. Okay, so that's that one down. So we got that little assumption out of the way. Now we can try to, so we have this free homotopy of loops, that works. So we've got that down. Now what we want to do is justify this condition, actually, this whole thing. So let's do that. We can also do that in the integral section, since that's related. Okay, so we can say let C subset to A be convex, and sigma subset to C be a loop. Contour. Actually, we can just say any contour. And X be in C. Okay, so C is convex, X be in C, and sigma subset C be contour with P1 of sigma never equal to P1 of X. And for any R in 0, 1, the loop, sorry, we can say we have a free homotopy of sigma and, okay, we have X plus sigma minus X times R, freely homotopic in C intersect A star plus X. Okay, let's try that. So we already wrote a proof for this, actually. And we can just take that. That would be this function. So I'll put this up in the integral section. That would be right up here. Okay, so we can say f t. Actually, let's do this way. Okay. Okay, so I've just modified this proof a little bit. So we have this function, we're using this, stay in C, f stays in C as a convex sum. So r is greater than 0, then this. We can actually just say r is greater than 0, and p1 of f blah blah is not equal. Okay, cool. So that's that. So we can probably put a lot of our theorems for these up here, if you would like. Okay, so let's go back to, we were working on this other theorem to try to prove that if we have these two things, that they're homotopic. So let's do this a little differently. We'll do a sort of intermediary proof. We'll say let C subset to A, B convex, and sigma, gamma, B subset to what do we have over here, actually? Okay, subset to C, B, actually I'm going to say C cap A star plus X. Okay, so we'll just have them as loops. Then, also with both P1 sigma and P1 gamma having turning number 1 about X. Turning number 1 about X. Okay. Um, okay. Where is this? Oh, I put it in the wrong spot. This should be down here. Okay. Okay, nice. X. Do instead of C, we do S. Okay. So let's see. So now we want to do this proof. So we want to show, so we've already sort of done this lemma, I guess I can call this lemma, for these, we've already done this lemma for these, yes, for this contraction. So we want to try to do this full proof for having, so we have two loops, their projection has turning number 1, and they're fairly, we want to prove that they're fairly homotopic in this punctured set, in this punctured neighborhood. So to do that, I think what we can do is, we can say, find 3 points A, B, C. We can say put these just in the sigma curve such that the triangle delta, which is A to B, B to C, C to A again, it also has, actually we can say take any 3 points ABC and sigma such that this triangle, then the triangle delta as these things must have delta subset to S, since S is convex. And then we can say select ABC such that the triangle P1 of delta is has the point P1 of X in its interior. This can be done by selecting points off the sigma curve if necessary. Actually, we can say well, let's see, what type of did we make? There. Okay, so we pick this triangle, and then what we're going to say is we're going to say we first take the case where P1 of sigma and P1 of delta, or sorry, gamma, are both subset to the interior of delta. Or rather, we can be a little more generous with this. We could say, using our lemma, we may contract sigma gamma to assume that the projections P1 gamma are close enough to P1 of X so that they are subset to the interior of delta. Okay, so we've placed these inside delta. Okay. And now what we want to do is we want to try to find a way. We want to try to find a way to turn this into a two-dimensional case. Or we could maybe just prove it manually. I really don't want to do that, though. Actually, no, this is fine. This triangle delta implies the existence of a plane. It's a simplex, actually. So we can just, if we can just project these onto that simplex, I think that's fine. Okay, so they're subsets to the interior of delta. So now we can say, or we could do another lemma if we wanted. So let's try this. So we'll say, let S be subset to A, and actually we can say let delta subset A be a 2 simplex. No, this won't work either. I'll just do it straightforwardly. We can consider, we'll do, okay, how are we going to break this down as a projection? Maybe there's a more powerful theorem in topology that would prove this. Okay, well, we've been going for a few hours now. I think I'm gonna stop this here, and then I'm gonna eat lunch, and then we will come back in, I think, an hour or so, and I'll think on this one to try and figure it out. Thanks for watching today, as always. Yes, this problem is very difficult, so we'll have to think on this. But we'll take a break for an hour, and we'll come back in an hour or so. So anyway, I will see you then.